Hello guys, welcome to your next video lesson. Again, this PowerPoint's available for you, as is a supplemental worksheet that kind of goes with this a little bit later on that might be pretty useful to you to have printed out. We're going to start off with this problem right here where you're solving. This might look familiar. So I want you to think about and maybe pause the video and try this on your own before I'm doing it with you or for you. But how do you go about solving this for x? Right? So in this first one, the entire log is being squared, whereas in this second one, just the argument is squared. Right? So for this one right here, I can, let me done something. I can bring that down. And I've got log base 3 of x. The whole thing is squared plus 2 log base 3 of x plus 1 equals 0. I would hope and probably assume that this looks a little bit familiar to us, right? It looks like a quadratic equation. And I'm going to do what I'm going to refer to as z substitution. So I'm going to go over here on the side and say, well, z is going to equal to log base 3 of x, right? And I'm going to come back to that idea at the end. And then for now, okay, well, I can say z squared plus 2z plus 1 equals 0. And I can factor that, right? So z, what is it? Plus 1 and z plus 1, oh, look, it's the same factor, equals 0. So z must be equal to negative 1. So what that means is log base 3 of x must be equal to negative 1, right? So if I'm going to read this, the exponent that turns 3 into x is negative 1. So the exponent that turns 3 into x is negative 1. Well, 3 to the negative first power is 1/3. Right? So I looked and saw that, oh, this looks like a quadratic. So I used, and you don't have to use z, you can use whatever letter makes you happiest. But that is the idea of what we're doing there. We did do this problem in an earlier lesson, but hopefully we recognized the pattern now, because it was a pretty challenging one as when we did it earlier. So, oh look, it comes up, but I already did it. What we're going to be looking at today, and we're going to kind of transition a little bit away. We did a lot with solving and simplifying and the properties and all of that, and we're going to take a look at graphing. And notice I'm saying without the help of a graphing calculator. While I think, and I feel like I emphasized this all the time when I had you guys in front of me, while I think it's extremely valuable and helpful to use your calculator and use an application like Desmos to check your work, I want you to understand and really have an in-depth understanding of what a logarithmic function, exponential function look like and why they look like that and how we can develop points and how we can recognize patterns as opposed to just relying completely on a calculator. So I encourage you to use it to check. I think that's a fantastic idea. And we're also, after we've sketched them, and we're not going to do any transformations today, these are just the straight graphs of what does it look like. We are going to be identifying critical values and features, which we've done a number of times. So I will go through and list out the critical features and values that I'm talking about or looking at. But you can maybe start to think to yourself or even pause the video now and like list them out and see as we get later into the video, did you miss any? Okay. So we're going to start off with these two. So I'm going to graph, label, and I don't know how many characteristics I'm going to list, but I'm going to at least talk about them, okay? So I'm going to start over here with y equals 4 to the power of x. And if you did watch the videos earlier, the supplemental resources from Unit 7a about graphing exponential functions, you remember me plugging in values. And what I had said was we're going to do 0, 1, because if you plug in 0, 4 to the 0 power is 1. Anything to the 0 power is 1. And then 1b, because if I plug in 1, I just get what the base is. And those 2 points are enough because we know what the graph looks like. So I'm going to plot the point 0, 1 and 1, 4. And then I have to graph something else, right? This, no matter how small my x value gets, how negative it gets, you're just going to make this a fraction, right? It's never actually going to get to 0 because we have this asymptote at 0. So I'm going to graph that and I'm going to label that. That's y equals 0. And then I'm going to sketch it, right? So that's going to approach 0. It's never going to actually get there. That is what the graph of an exponential function looks like. This one, and I don't love how I wrote this. I wish I had that in parentheses. I'm going to do the same thing. Oh, I have 0, 1, 1, whatever the base is, 1/4. So 0, 1, 1, 1/4. That's a sketch. And then again, no matter how big now your exponent gets, as your exponent gets bigger, your output's going to get smaller. No matter how big it gets, it's never going to actually become negative. Think about even like with log functions that we're talking about, your argument, the outcome of this is never actually going to be negative. It's always got to be greater than 0. This is why. So make those connections. Whoa. I don't love that, but I can't really fix it. It got a little wild. Oh, there, that's better. Just ignore this. Right? And this is again at y equals 0. So if I wanted to list out a few characteristics or talk about a few, let's chat about a few of them. Unclear if this is going to let me change colors. What color should we use? Blue. Let's use blue. What's the domain of this? All real numbers. What's the domain of this? All real numbers. What about the range? The range is going to go from 0 to infinity, non-inclusive. Or you could say y is greater than 0, right? Same thing here, actually. It's going to go from the asymptote to infinity because it's happening above, or I could say y is greater than 0. This one is increasing on the entire domain, right? It's increasing from negative infinity to infinity. What about this one, though? It's decreasing from negative infinity to infinity because this one is growth. No, that's messy. And this one is decay. What else? These are both continuous functions, right? They're both concave up. They both have asymptotes at y equals 0. They just have horizontal asymptotes. Neither one. No x-intercept for either. Right? They both have a y-intercept at 0, 1. Y-intercept at 0, 1. I'm sure I'm missing something. No x-intercept, increasing, decreasing domain range. I hit on some key points. They're both functions. They're both one-to-one functions, which would mean that their inverses would be functions. We will talk about more characteristics later, but I think I hit on like the key ones for this. So this is what exponential growth and exponential decay look like. We're not looking at transformations today, or in this lesson. We're going to look at that later. So I just want you to get the basis of it. That 0, 1, 1b is really where I'm going to build from. So the definition of an exponential function, y equals b to the power of x is an exponential function if b is greater than 0 and b does not equal 1, right? Oh, like a log function. Wasn't that the definition of a logarithm? The base had to be greater than 0 and it could not equal to 1. Oh, you should notice a lot of consistencies. Right? So, ooh, wow, that is hard to see. Wait, you can evaluate -5 to the power of 3. Right? That is a possible thing to evaluate, right? That's going to give you, what is that, -125, I believe. Right? So that probably brings up some questions. The reason that is not an exponential function, so you're able to do that, but it's not an exponential function because watch this. If you have, let's say, we're going to do negative 5 to the power of x. If you plug in 0, you're going to get 1. If you plug in 1, you're going to get negative 5. If you plug in 2, you're going to get positive 25. If you plug in 3, you're going to get negative 125, right? So it's going to like go between negative and positive. It's just not going to be an exponential function. So not to say you can't do it. It's just saying it is by definition not an exponential function, right? So, oh darn. Let's see, can you guys read this? Wait, I can evaluate 1 to the power of 3, but right? I think we talked about this one. Why is 1 to the power of x not exponential function? Right? No matter what you plug in, this is just equivalent to 1, so that's just a horizontal line, not an exponential function. Exponential functions have to be that shape of a swoosh, right? So these are things that are possible. They're just by definition not an exponential function, right? So this is what it's going to look like if b is greater than 1, right? That's like your growth factor. If b is between 0 and 1, because it's not going to be less than 1, so like a fraction between 0 and 1, that's going to actually b is your decay factor, right? So it's what it's going to be multiplied. b is like your multiplier. Like how do you what are you multiplying by to get from one value to the next? Characteristics list, let's see. Let's see how I did. I did domain. I did range. I talked about how it was a function and how it was one-to-one. I almost missed that, but I said it right at the end. I think I said it was continuous. I'm going to pretend I did. I talked about x-intercept. I talked about y-intercept. I didn't talk about maximum or minimums. An exponential function does not have any, right? Same thing with minimums. These are the extrema. I talked about increasing. I talked about decreasing. It's going to be one or the other. I talked about concavity, right? And I talked about the equation of the asymptote or asymptotes. For an exponential function, we're only going to have one, right? When we were dealing with rational functions, we had more than one. We had to deal with horizontal. We had to deal with vertical. For the equation of an asymptote, for an exponential function, you're just going to have one horizontal asymptote for exponential. Fantastic. So here are your list of characteristics. Now we're going to look at log base 5, and maybe you know why. We're going to look at log base 5 of x and 5 to the power of x, and we're going to analyze these a little bit closer. Okay, so we're going to do this. Hopefully remember that this is composition of functions. Right, so if I do f of g of x, so I'm going to plug g of x in to f of x, right? So if I do f of g of x, sometimes this looks like f of g of x. I would get log base 5 of, and instead of x, I'm going to write 5 to the power of x. Like a new pen color, maybe a nice magenta. So I'm going to use the bring down property, and I'm going to bring that out in front. You might already know what's going to happen, but I'm going to do that anyways. X times log base 5 of 5. Well, this piece of it's just 1, so I just get x. Right, so I got x for this. What about g of f of x? Sometimes written as g of f of x. So for this, I have g, oh no, I'm going to start with g of x, 5 to the power of log base 5 of x. We did some like this, right? So if you do 5 to the power of log base 5, those are like going to cancel, and you're just going to get x again. You got x for both of them. So if we remember, what does that actually mean? If you compose blank, your outcome is x. What is that? That goes all the way back to like way at the beginning of the year. Well, what are some of the fun facts of inverses? This was definitely not number 1. I think this was like number 4. But if you compose a function and its inverse, and the outcome is x, then the outcome is x. If you compose two functions and you get x, that means they cancel each other out, right? Like you did something and then you undid it. Whoa. That means that these are inverses. So they are inverses, right? Compose a function its inverse, you should get x. I don't know if it was number 1. Let's talk about some of the other fun facts. Some of the other ones, what happens? You just switch the variables. And that one might even take you all the way back to geometry last year, right? So let's say I switch the variables. Let's say I took g of x. So I've got y equals 5 to the power of x, and then I switched x and y. I don't know what this is, but I want to use it. So I'm going to switch x and y. So I've got x equals 5 to the power of y. Well, in order to solve for y, I'm going to have to do, right, the exponent that turns 5 into x is y. The exponent that turns 5 into x is y. Whoa. That's f of x, right? So you just got log base 5 of x is f of x. So we switch the variables. What's going to be true about the graphs of inverses? It's a question mark. They reflect over the line y equals x, right? That diagonal line. It's if you folded it on that diagonal line, right? So if I had a graph, well, this is the line y equals x. If you reflect over that, that is like those two functions are inverses. So, which leads me, right? So we're going to build on, and maybe you don't have very much background knowledge in exponential functions. It's fine. We're going to kind of learn those in conjunction with logarithmic functions because they are inverses of each other. So what is the inverse of f of x right here? Oh, 7 to the power of x. What about the inverse of t of x, right? And this is inverse notation. 4.2 to the power of x. What about ln of x? Well, that's the same thing as log base e of x. So that's e to the power of x. That one's cool because find it in your calculator. If you do second ln, you get e to the power of x. So it's telling you that they're inverses. That one's always pretty cool. So I like to approach logarithmic functions thinking about the exponential function first, and then just thinking about it in terms of an inverse instead of trying to create something totally separate, right? So this is really neat that we can do this. So we're going to start with just the base function b to the power of x. So just like I said, we're going to plot the point 0, 1, right, which is the y-intercept, or the starting point. And then we're going to plot the point 1b, right? So that's like the growth or decay factor. And then we know what the function looks like, so we're able to do that. What is the x-intercept? None. Why? There is an asymptote at y equals 0. Right, so if I now have these points for this exponential function as 0, 1, 1b, if I'm going to think about its inverse, which is log base b of x, well, I'm just going to reverse everything, right? So I'm going to get a new color. So I'm going to start it. I'm not going to start it at the point 0, 1. I'm going to start it at the point 1, 0, right? Which is its starting point, but it's actually not going to be your y-intercept. It's going to be your x-intercept. And then instead of plotting the point 1b, I'm going to plot the point b1. It's still like your growth and decay factor, right? Here, I'm not going to ask you, is there an x-intercept? I'm going to ask you, we know there's an x-intercept. We started with it. I'm going to ask you, is there a y-intercept? No, because there is an asymptote where? At x equals 0, right? So if you start your thinking with the exponential function and then move it to the inverse piece, you can build on it, right? So you're learning them both together ideally, right? So your x and y, your variables are switching. So if we want to graph y equals 7 to the power of x, here are some points, right? I care mostly about these two, but we can still look at them all, right? So I'll plot a point. It's not what I wanted to do. I'll plot a point at 0, 1, and 1, 2, 3, 4, 5, 6, 7. Oh, I wanted it to be nice, but that's okay. So then I have my asymptote at y equals 0, right? So then we're going to look at the inverse of this function, which is y equals log base 7 of x. And I'm going to flip these, right? So now I'm going to focus in on these 2 points, 1, 0, 7, 1, because that's all that's happening. So 1, 0, 7, 1. Oh, it's going to reflect over this line. So kind of think about, well, what is it going to look like? Because sometimes it is hard to visualize it, and that's why I like to think about what does the exponential function look like. So you're thinking of it in terms of a reflection. I'm going to have an asymptote here at x equals 0. Oh, sorry, x equals 0. And then I can draw that swoosh, and you can kind of see that these are a reflection over that diagonal line. As far as that logarithmic function, I know it's a little bit hard because I just clicked off of the screen, but hopefully you graphed on your own. And this is the worksheet. Like, this is the supplemental worksheet. I should have said that earlier. So if I'm going to graph this first one, b to the power of x, where b is greater than 0, right? So I was dealing with 7 to the power of x, and then here I was dealing with log base 7 of x, right? So my b is greater than 0 for both of these. The domain is all real numbers. That range was going to be from 0 to infinity. Yes, to all of them. Was there an x-intercept? None, or I could have said the empty set. Was there a y-intercept? Yes, it's 0, 1. No, no, it's increasing over the entire domain. It's not decreasing. It's concave up over the entire domain. It's not concave down, and there was an asymptote at, what was it? Y equals 0. It's like the parent function. For this one, my range is not, my domain is not all real numbers now, right? So I had that vertical asymptote at 0, at x equals 0. So this is going to be from 0 to infinity, and then your range is now all real numbers, right? So look at what happened there. Yes, right? That's why we were able to go between these two. This one has an x-intercept at 0, 1, and no y-intercept. No maximum, no minimum. It's also increasing. It's also not decreasing. This is going to be concave down, right? So it had like this swoosh shape. So it was concave down. And the asymptote is at x equals 0, right? So look at some of those patterns there so that you can think more logically through it. So now we're going to look at it where b is between 0 and 1. Right, so we're going to graph this. So again, I'm going to focus in on these 2 points, but it is good to know like what else is happening. So you've got 0, 1 still, but then 1, 1, 7, and it's going to decay. So it should be getting exponentially close to 0, but I never actually get to it. Ooh, that's not very nice. And your asymptote is still at y equals 0. Right, so if we graph the inverse of that, which is y equals log base 1, 7, I'm going to switch the x and y, but I'm still going to focus in on those first two because I want to know where are these points going. It should still reflect over that line y equals x. So this one's a little bit harder to see. And you didn't, no, I don't. So I've got a point at 1, 0. I have a point at, what is that? 1/7, 1, sorry. And I have an asymptote at x equals 0, and it's going to decay like that. So you can kind of see, and mine's not the greatest of all graphs, but this point ended up here. This point ended up here. You can see like where they went. And if I were to draw that line, it is reflecting over it. It's like this swoosh ends up over here. Mine's not very great, but it's all approximation for that because that 1/7, right? So a little bit harder to see. So you kind of have to see that for a log function that's decaying, it's going to go like swoosh. And a log function that is not decaying, it's growing, it's going to go like swoosh. So this is going to be where b is greater than 0, and this is where it's going to go between 0 and 1. So if we look at these characteristics, and again, a little bit hard, hopefully you got it down on your paper so that you can fill this in. The domain here is still going to be all real numbers, right? The range is still going to be from 0 to infinity. It's still a function. It's one-to-one and it's continuous. There's still no x-intercept, and the y-intercept is still 0, 1. Still no max or min. It's now not increasing, right? It's decreasing over that entire domain. It was still concave up, right? Yeah. It's not concave down, and the asymptote is still at y equals 0, right? So really the things that changed there were just these, right? Increasing and decreasing interval. For a log function, so what did that look like? It looked like this, right? Was that what it looked like? Now I'm blanking. Oh, I wish I could go back and see it, but then this is going to get erased. It's okay. So between 0 and 1, the domain is now from 0 to infinity. The range is all real numbers. It is a function. It is one-to-one. There is an x-intercept. It's at 1, 0, right? There is no x-intercept. There's no max. There's no min. Let's do this. So let me sketch myself a picture of it again. So that one was 1/7, right? So we had 1/7, and then here, and it looked like this, right? So that's gonna be decreasing. So we're gonna be decreasing, not increasing. We're gonna be decreasing from negative infinity to infinity, and that is concave up, isn't it? It's not concave down, and your asymptote's gonna be at x equals 0. Fantastic. So what we just did in this lesson, and we did not cover, this did not get very intense. I'm going to go into the transformations on the next one. I really didn't have any supplemental practice or suggested homework or any work. I think it's probably in your best interest to just go ahead and move on to the next lesson after this one so that you're then practicing with transformations, not just graphing in isolation. I just wanted to have an opportunity to introduce it. So we just graphed. So we sketched, labeled, and looked at critical values and features of both exponential and logarithmic functions, right? So if you remember, for an exponential, it's 0, 1, 1b. And for a logarithmic, it is 1, 0, b1, right? So this is for log, this is for exponent. And an exponential function has y equals 0 as your asymptote. Well, that's not a great abbreviation. And x equals 0 for a logarithmic for your asymptote. Whoa. I encourage you again to start moving on to the next topic and kind of watch these two together and do the work that goes with this together as far as graphing and looking at those transformations. Thanks, guys. If you have any questions, please, of course, as always, let me know. And if you need to go back and watch anything or print anything, please, by all means, do that. If I made a mistake, call me out. Thanks.